Display power consumption is an emerging concern for untethered XR devices. As such, many power-saving algorithms have been proposed. However, prior art measures the image quality impact of these techniques in many different ways. We introduced Project PEA-PODs, a perceptual evaluation of algorithms for power optimization in XR displays. We set out to measure the perceptual impact of display mapping techniques on a unified perceptual scale across several display types. We first discussed display power models we fit to physical measurements. We used the linear OLED power model from Dunkerjov et al. For the Vive Pro I, which varies significantly with color. Our modeling of the Quest Pro LC panel and backlight unit, or BLU, measurements show little variation in LC panel power, so color has minimal impact on LC display power. We also modeled two BLU driving schemes. Global dimming, which is an approach that sets all BLU LEDs to the same value, and local dimming, which allows for control of individual LEDs. For local dimming, we implemented a heuristic using the measured Quest Pro point spread function to determine BLU LED intensities. We now discuss the 6 display mappings studied in this work. This includes traditional methods like uniform dimming, which globally darkens the display, and clipping, which only decreases the brightness of highlights. We also explored techniques for XR displays. Dichoptic dimming only dims the left eye display in a binocular device, and brightness roll-off is an eye-tracked method which dims more aggressively in the periphery. Color remapping methods were also studied, such as white point shift, which modifies the display white point power optimally, and color foveation, which applies more aggressive color modulation in the periphery. We set out to study how applying these methods to images affects their perceived quality. To determine appropriate stimulus intensities to use in the main study, we conducted a pre-pilot using a Quest procedure and 2 additional pilots with the same procedure as the main study. After each pilot, magnitudes at 1, 2, and 3 JNDs were extrapolated and used as intensities in the next pilot. The main study was implemented with a 2-interval forced choice procedure with the reference included. The user's task was to select out of 2 videos which one had fewer visible distortions or was closer to the reference video. This example video is representative of some of the stimuli that are presented to users in the main study. The data collected in the main study were scaled in unified perceptual units of just objectionable difference, or JOD. We can now plot JOD scores against power savings for each method. We fit transfer functions to the JOD versus power savings data, which allows us to make decisions about which display mappings will be useful for a particular display type under a perceptual constraint. For example, in eye-tracked OLED and local dimming LC displays, brightness roll-off produces the most power savings with the least visible distortion, whereas in non-eye-tracked displays, the best techniques are uniform and dichoptic dimming for all 3 display types. We can use these results to explore several display power-oriented applications. The first involves modifying the display primaries to save power. This figure compares the color difference versus power savings for the primaries sampled in this study. This data is compared to the power savings of white point shift with the intensities used in the main user study. We selected power optimal 3, 4, and 5 primary combinations that minimize average color difference score. An often ignored constraint is the power consumed by the eye tracker itself. With this consideration, brightness roll-off cannot save more power than the best non-eye track technique. However, if eye tracking is a system requirement, brightness roll-off can offset the ideal eye tracker power consumption at -1 JOD in the HTC Vive Pro I and almost half the ideal eye tracker power consumption in the Quest Pro. Thank you.